Hello. Today we'll be dealing with the rest of the things associated, especially the elements associated with an electrical circuit for the conduction of electricity. One of them being the cell, which carries a potential difference across it, termed as the EMF of the cell. Now, as before going over to this topic, we had last discussed about the temperature coefficient of resistance, and in that temperature coefficient of resistance, as you know, that we had obtained an equation where R final was equal to R initial times of 1 plus alpha, that is the temperature coefficient of resistance, multiplied with the difference in temperature, that is del theta being the difference in temperature in this case. Now, if you observe this equation, what you will find is that as Ri gets multiplied with the terms inside the bracket, as is the case with the original form of the equation, you have a thing on the left hand side, that is Rf, which is varying, and it's varying with respect to the initial resistance, that is Ri. It is also varying with the change in temperature. Now, if we are to plot a graph regarding this variation of resistance with respect to temperature, we have the resistance on the dependent axis, and it depends on the temperature, which is in the independent axis. The temperature is independently increasing, while the resistance depends on the increase in temperature or the change in temperature. Now, the initial resistance over here has some value, let us say that is Ri, that we have considered, and Ri increases, and as it increases, as you can see, because you have an equation, we have this in the y-axis, this in the x-axis, that is the variation in temperature. Anything multiplied, now as you observe this, as you do this, plot this graph, you will find it to be a straight line. So obviously this is a straight line equation where you have a slope in the form of m, and you have a y-intercept in the form of Ri, that is c. So this is the y-intercept that we have obtained. We have shown it as Ri on the graph, and then obviously the plot giving the variation of resistance with respect to temperature, it will achieve a final value at a given temperature. Now, if we are to observe the slope of this graph, the slope usually represented by m is m equals, now what is the value of the slope over here? M equals Ri times of alpha. Knowing the value of Ri, knowing the value of the slope, one can obtain the temperature coefficient of resistance from this graph. So that is the way to obtain the value of the temperature coefficient of resistance. Usually the temperature coefficient of resistance, the resistivity is of the order of 10 to the power minus 8, that is for aluminium, 10 to the power minus 8 to 10 to the power minus 11 in the lower range, and accordingly you have the value of alpha nearly 10 to the power minus 6, varying between 10 to the power minus 6 to about 10 to the power uh, minus 4 to minus 8 to be precise. It can vary over a huge range, but that is to be experimentally determined. You can use various uh, apparatus for it in order to obtain The setup is usually it usually consists of a thermometer and where you can measure the change in temperature over given period of time for the variation in the current and the resistance as well. From the variation of current, you can obtain the resistance. Okay, now we move over to the cell, the case of cell, or the arrangement of cells which comprise or which are collectively known as battery. So you have a cell, and the cell has what we call is an EMF. Now, a cell is usually made up of positive and negative electrodes, and it has an electrolytic solution between those electrodes, or the electrodes or even rods are placed within that electrolytic solution, and the ions start dissociating as the electricity is conducted. But here it is the ions, the electrolytic solution comprises of ions, dissociated ions, and they maintain a certain potential difference across this entire arrangement of the cell. Now, in order to maintain this potential difference across the cell, the mechanism that is done, in this case the internal mechanism, that exerts forces on the charges of the material, right? This force that is given to supposedly a positive charge, if I can consider, or even a negative charge, the positive ions and the negative ions coexist in this case, and the negative charges are pushed towards the negative terminal, while the positive charges will be pushed towards the positive terminal. That is the mechanism of the cell, where it maintains a certain potential difference, V, if I can say. V is the potential difference. Now, the force that is applied in order to maintain this potential difference, it does some work over the length of the cell. Let this length be d. So the force multiplied with the distance across the cell does some work. Now this work that is done per unit positive charge, we always consider the positive charge in case of definitions, or in case of measurements. This work done per unit charge is what we call as the EMF, and obviously that work will obviously be equal to the potential difference, because there is nothing else where the potential or the EMF, that is to say, is getting distributed, because we are considering wholly the cell itself, not any external circuit as of now. The potentials are maintained across the electrodes, so there is no distribution of force or work outside the cell as of now. This therefore is known as the EMF. Now EMF is the abbreviation for electromotive force, but however the force thing is not what we are considering over here. What we are considering is the potential difference maintained uh, across the electrodes that are present or that are dipped within the cell. So the wording, the phrase electromotive force is not considered. We use the abbreviated term, that is EMF, in this case every time we are uh, obtaining the potential difference within the cell when it is not connected to any external circuit, and that is equal to the work done per unit test charge, per unit charge, in order to maintain that potential difference. That is the work of a cell. Now, as this cell, usually the cell is symbolized as this, This is the symbol for the cell. It has a positive terminal, it has a negative terminal, and the chemicals in between, the electrolytic solution, and this is just a representation. But however, because you know that there will be lots and lots of ions, positive and negative, and as these ions, as I represent them by dots within that diagram that I have drawn, now these ions, as they tend to move across the cell, rearranging themselves, the positive ions on the positive side and negative ions on the negative side, to maintain the potential difference, obviously they are going to collide with one another, and that is going to provide some kind of resistance or obstruction to their flow, which we popularly call as the internal resistance of the cell. The internal resistance. Now, the internal resistance, usually the external resistance is denoted by the capital R, this internal resistance by small r. The internal resistance of the cell is usually denoted, if this is the cell that I have drawn over there symbolically, the internal resistance is just represented like that within the cell, or it is represented near to the cell for a given circuit diagram. This comprises of the entire cell and its internal resistance. So that is the way we represent the cell in a circuit with a internal resistance. However, the internal resistance is mostly neglected when we are considering the motion of the charge from the positive charge from the negative terminal to the positive side, because that is the work done. We are concerned about the work when we are considering the motion of the charge from one end to the other in order to maintain the potential difference. Whereas if this thing is connected to an external circuit, that is a cell, I'm drawing that entire circuit that I can consider right now, the EMF of the cell is the total potential difference that is present across the cell. Now this cell acts as a source of potential difference to an external circuit. Now the external circuit is driven by a cell, obviously, because an external circuit needs some potential difference to operate. As far as Ohm's law is concerned, it tells us that there must be a potential difference in order that there is a flow of current across a given conductor. So we have this EMF over there, and that is provided to the external circuit, which comprises of a resistance. Now as you observe this, I must add that the resistance that is present in the external circuit is present actually throughout the circuit, right from the end where the cell now I have marked as positive to this point where I have marked the cell as negative. Obviously this is the arrangement of the cell, which comprises of the internal resistance within it represented outside it. Now that entire wire, that entire conducting wire that is present throughout the length, that possesses resistance across it, but we need not represent the resistance entirely throughout the wire, conducting wire. We can represent it just there, by those zigzag lines. That is the way of representation of representing resistance across a given circuit externally. But as I said, the entire wire is providing resistance to the flow of charge. Now as we consider the flow of current across the circuit, so this is the current that has developed, that is I. Now this current, as it moves across this resistance, it may so happen that I may consider a resistor at that point as well. So it's the same way of saying it's the or rather the different way of saying the same thing. So as the current moves across that resistance that I have shown over there, the capital resistance, we obtain a potential difference across it, and as far as the Ohm's law is concerned, we have V, that is the potential difference, is equal to the current that is flowing across the circuit multiplied with the resistance that is present in the external circuit. But we also have an internal resistance which is at present in series with the external resistance, as you can see. And because we have this external resistance and the current must flow across the entire arrangement for the circuit to get completed, obviously will be having a certain potential difference across the internal resistance as well. And this potential difference is I times of R. We can give it a notation as a V dash. Now V and V dash are possible only because of the EMF that is available in the circuit, and EMF is not wasted considering the conservation of energy. So this EMF that is provided is distributed across the circuit in the form of V and V dash, and it's obviously, as I said, based on the conservation of energy. There is no loss in potential. So this can be further extended or written explicitly as IR plus I times of small r, that is the internal resistance. And so from that what we have is, we have IR to be equal to E minus IR, that is for V. And also we can have the value of internal resistance as well, that is E minus IR or V divided by the total current that is flowing across the circuit. This is the expression which you can use to obtain the value of the internal resistance in for a given cell. And this is when the cell is discharging some energy, or it is, yes, of course it is electrical energy throughout. So this is the process of discharging, where the EMF is provided across the circuit, which provides it with a potential difference, net potential difference. That potential difference which was maintained across the cell is now available to the external circuit by the conducting wire that we have considered, and that EMF is getting distributed across the external resistance as well as the internal resistance in the form of potential difference across each of them. But this is, however, in case of a discharging of a cell. Now consider the case of charging of a cell. Now from this, obviously you have that this equation that you have over there, now that I'm rounding off, because you are adding something to V, you are getting the EMF. What you are adding is V dash to it as far as the equation part is concerned. So what we know is that the EMF in this case is greater than the potential difference across the resistance, and this is the case of discharging, as I said. Now consider the case of charging of a cell. Now as a cell is charged, or it needs to get charged, it is connected to a supply. The supply being, it can be your household circuit supply of 220 volts, or in the other countries you have it to be 110 volts, whatever may be the case. But as you connect this EMF, which is obviously having a lesser value, you connect it to an external powerful circuit, say the electrical supply of your house, in order to charge it. So in that case you have the equation as because you have the internal resistance in that case, so you have the equation. Now this part of the equation, if I say this part of the equation, you have from that E minus V divided is equal to IR, is what you have in this case. This minus now changes to, or you have this V to be equal to E minus IR. you have the V to be equal to E minus IR. The only thing that changes is that instead of that minus, you have now plus, because you are providing it with a potential difference. So the minus changes to plus in this case. And as a result of that, what you have, the equation changes. The equation obviously changes to something different, which is obviously E plus IR is equal to V. And here, as you can see, that V is greater than E, and this is the case of charging of a cell. That was the case of discharging of a cell. We are mainly concerned about the discharging process, where the cell is providing a certain amount of energy to the external circuit for it to operate. That's more or less a uh, small part of the devices that are to follow, the cell being one of them and its EMF. In the next video, we'll be dealing with the potential difference as well as the drop and gain of potential, and to add to that, we will be discussing the Kirchhoff's laws, and from that we will be obtaining the balanced condition of the Wheatstone bridge, as well as the condition for obtaining the resistance, unknown resistance in case of meter bridge, and also the potentiometer. The combination of resistances uh, and the combination of cells are also uh, in line uh, for the next videos, upcoming videos. Till then, thank you for watching.